Do you ever feel like math notation is tough, but programming makes more sense? Or maybe you get math easily but find it hard to read source code? The thing is, you might already understand both. You just don't realize that they are describing the same ideas, just with different symbols and styles. If you are new here, my name is Pavel. I work in game development and I'm a former graphics developer and researcher. I also have a PhD in computer science. On this channel, we explore computer science topics from both the theoretical and practical sides. Today, I'll share 10 mathematical concepts and how they directly map to programming ideas, specifically using examples from C++. Even if you don't write C++ yourself, the ideas still translate easily to any language. Let's start with the sigma symbol. In math, it means summing values over a range. For example, when we say the sum of I from 1 to n, what we really means is start at 1, go up to n, and keep adding each number to a total. In programming, this is exactly what a for loop does. Imagine you create a variable called sum and set it to 0. Then you loop from 1 to n, and on each step you add the current value of I to your sum. At the end, you've built up the total, just like in math. Next is the pi symbol, not to be confused with the number pi. This symbol is uppercase. In this context, pi represents a product, multiplying numbers in a sequence. So if sigma adds, pi multiplies. In programming, the logic is exactly the same. You create a variable called product and start it at 1. Then, as you loop through the numbers from 1 to n, you multiply each number into your product. By the end, you've accumulated a full product step by step. Let's talk about infinity. In math, infinity shows up in things like infinite sums, limits, or processes that never stop, like dividing numbers smaller and smaller forever. In programming, we express this using infinite loops. Loops that run endlessly unless we explicitly tell them to stop. For example, a loop that says while true is one that never ends on its own. It just keeps going, like an infinite series in math. We have to include a condition or break to exit the loop manually. For instance, when user hit escape. Otherwise, it runs forever. And what about empty set? In math, the empty set means a set with no elements. It's literally nothing, no members at all. You'll see this written as A equals the empty set. In programming, this maps directly to empty data structures. You might declare a vector or a set, but not put anything in it yet. This is the same idea, an empty collection. It exists but has zero content. It might be an empty inventory just waiting for a player to find loot. Next is the concept of element of. In math, when we say X is an element of set A, we are saying that X is inside the set. In programming, we do the same thing when we check whether a value is inside the list or container. For example, we might search through a vector or a set and see if we can find X. If we find it, we know X is a part of that collection. This is what's called a membership check. Now let's look at the universal quantifier, for all. In math, this symbol tells us that something is true for every item in a set. For example, for all x in A, x is greater than 0. In programming, we often check this using a function that goes through each item in collection and tests whether a condition is true. If every single item passes the test, then we say the condition holds for all of them. So if we are checking whether all numbers are positive, we look through the collection and confirm that every value is greater than 0. If even one fails, the whole test fails. We often use lambda functions here, short anonymous inline functions that makes this kind of test easy to write. They might look complicated at first, but they are just compact ways of saying, this is what I want to check. We'll see them again in the next example and later. Now the opposite. There exists. In math, this means at least one element in a set satisfies a condition. You'll see something like, there exists an x in A such that x is less than 0. In programming, we call this an existence check. We loop through a collection and ask, is there any element that satisfies this condition? If we find even one that works, we return true. This is often done with functions that says any of in C++ and standard library, meaning is the condition true for any of the elements? Now we get to logic. The implies symbol means if this, then that. For example, if x is greater than 0, then x is positive. In programming, this is literally what an if statement is. You check a condition, and if it's true, then you do something. It's a direct mapping from mathematical logic to program control flow. If the condition is false, you might skip the action entirely. So the if-then logic from math becomes executable code. The maps_to symbol is used in math when defining functions. For example, f maps x to x squared means that f is a function that takes x and returns x times x. In modern programming, especially in C++ and other functional style languages, we often use lambda functions for this. Finally, let's talk about contradiction, the symbol for an impossible or undefined state. In math, this shows up in cases like if x equals 0, then we have a contradiction, like trying to divide by 0. In programming, we handle these situations by throwing an error or an exception. For example, if a function tries to divide by 0, we can raise an exception to signal that something has gone wrong. This is how we handle logical contradictions. The program stops and lets us know there's a problem, just like in math when an expression becomes undefined. So there you have it. Math and programming share a deep connection. Once you start to see how concepts in one domain match concepts in the other, everything becomes a little less mysterious. That's it for today. If you enjoy this kind of content and want to see more in the future, hit the subscribe button. Thanks for watching. See you next time.